Hello, everyone. Welcome back. Hope you enjoyed a nice break. And it's time for our last speaker of the day. Victor Martinez is an MD and lead data scientist at State Street. His recent work at State Street consists of applying AI methodologies for portfolio management, multi-asset pricing focusing on liquidity, analysis of flow, and correlation risk. He also worked as a Quantitative Director Analyst, focusing in mathematical finance methods for asset pricing and application to illiquid asset valuations, derivatives, risk management, business valuation, and study of fund dynamics. Prior to State Street, Victor served as Professor of Finance for the Zicklin School of Business at Baruch College in the University of New York, where his research included option theory, asset pricing, news analysis, M&A, and mathematical finance. He also worked for various hedge funds, including Citadel, Archelon, and Tradelink, focusing in quantitative trading strategies and risk management. He holds a PhD in theoretical physics from the Massachusetts Institute of Technology and a BS in physics and mathematics from Stony Brook University at State University of New York. Please welcome our last speaker of the day, Victor Martinez.
Thank you. Thank you. Thanks for inviting me. And I don't know if it's a good thing to be the last speaker or a bad thing, or a positive thing, but I'll try to not bore you too much. So my talk is going to be a little bit kind of a survey more than a very technical talk. There's going to put some formulas in there, but the idea is to get into where AI has been so successful, and then what is the situation in finance in terms of these methodologies and how they're actually working. So we saw a few talks today, and one of them was in pricing previously. And that kind of showed a little bit of the power of what AI can do. And some other applications of that had to do with risk, and then in some other aspects of time series analysis. But so far, most of the success in AI comes from the traditional things that we know, like image processing, language processing, and voice recognition, which have made significant, create a significant impact in different aspects for society these days. So what I wanted to do with this talk is to say, okay, where and why these things have been so successful, and where is it that they are being applied in finance, and why they are applied properly, and why not. So from that point of view, I'm going to try to be very descriptive, and then sort of walk through step by step of the things that I think the AI techniques why did they actually become so successful, and what is it that they're introducing or they're trying to solve. So that's kind of the agenda of my talk. One of the things that I wanted to mention also in terms of the previous talks that we have heard is that there was a lot of discussions about market efficiency. And there is an issue about, they say, well, if markets are going to be efficient, it's going to be very difficult in principle to come up with any model to predict prices in general. Because if markets are efficient, then there is no hope for us to be able to beat the market in general. And that's partially true, but there is a caveat to that effect, is that if we know how the markets become efficient, then we can either understand for risk purposes how the market gets to that efficiency level, or if we understand how the market starts from a certain state and move into an efficient state, then the ones who have actually algorithms to pick that kind of pattern, then they eventually can also make profits, making the markets also more efficient in that process. So that's kind of the idea. So let me just start with AI. Where is it that we have been successful? It's mostly image recognition, language processing, voice recognition. Why is it that they have been so successful? One of the things is that we have large amount of data. And these techniques have been amazingly good in processing large amounts of data. In finance, we have some of that, but we have data issues. But where these things haven't been applied too effectively is in multi-asset strategies and pricing large data sets. But the potential and the value of this is that when you look at very large multi-asset strategies and put them into these technologies, then there is some potential that some new a new revealing and phenomena might come and be revealed in this kind of analysis. The other part is multivariate time series. Again, the idea that markets are efficient and they are actually moving constantly to adapt to new market conditions makes the analysis of time series very challenging. But I will just go through some of the ideas about how can we actually look into that from a different perspective, from the multi-asset level or lens. So again, what is it that image recognition has been done to us? So I'm going to be focusing a lot of this in the image recognition part, figure out what is it that are the properties of that AI is bringing to that analysis, and then transfer that into the financial world. So for example, in large feature sets like images, you have the ability to handle multivariate kind of phenomenon, and then being able to combine it in a very structured way to detect patterns. So at the end of the day, AI is nothing but a pattern recognition tool. And then the type of patterns that can be revealed in the data, these techniques have proven to be very effective in identifying them. So one particular case is you have a car or a picture, and then decomposes the picture into structures. Now, those structures seem to be they get represented in a kind of a chain form, right? So one of the issues that happens in those particular patterns is that they have some kind of fractal structure. So that means that one structure gets formed, and that structure sort of builds on another structure, and then eventually composed what it seems to be a complicated, complex pattern. In some ways, when you reduce it to the basic elements, then you can start deciding the structure and the patterns that data reveals. So how does machine learning techniques work? Well, one thing is they start actually picking nonlinear effects. What do we mean by that? For example, if you have like a quadratic relation, right, you can have two hidden layers with two activation functions. And by combining those two hidden layers, you can actually start expressing and then getting a nonlinear relation by linearizing the space locally into this kind of patterns that the neural network be able to capture. Right? So the first effect is that it introduces nonlinear effects by linearizing the space locally. So that's one of the first things that these techniques do, right? So what is the next thing that they do? Well, they take those regions of space, right? Those regions of space, and then they start combining them in a non-local way. For example, this region of space might actually be talking to this, and then this neural network might allow to decide that structure, decide that connection. In a lot of the techniques in time series, for example, splines, or that effect is actually not possible. If you have like a spline, in terms of discretizing your space, localizing, and then do a small linear regressions on which the spline needs to be continuous. So in that way, it only connects spaces adjacent to each other. But in the sense of neural networks, you have the potential to connect or look for relations in which those parts of the space are not connected continuously. So that's another advantage of these effects. So what is the other feature that these structures allow you to come up with much more complex relations? The other part is that, and I guess that's where the TensorFlow comes in, it allows to manage those relations as tensor relations. Now that is important because, again, this is a way of looking at non-local, non-linear relations, and then they can localize them and then linearize them in some kind of powerful way, like metrics do in general. Right? And then the other part is it composes relations, right? So it takes one relation and then composes with another relation and another relation, and then by doing so, it can generate very complex patterns that you wouldn't be able to do otherwise. So there is that, it's what I call the compose or the chain reaction effect. Again, it's more like a fractal relation. You start with one simple relation, and then you build more relations on that space, and then this picks that kind of effect. And then you expand that to multivariables, and then you start seeing the power of all this complexity building into these networks. Right? So that's sort of how I intuitively kind of perceive the power of neural networks in general. Notice that I'm actually focusing mostly on neural nets, and because in my mind, that has been the most effective and more powerful techniques in the set of tools that machine learning has provided to us. So by doing so, right, we can take very fancy structures, very complex structures like faces, and then create very complex networks with deep layers, and then these techniques allow to pick those structures very effectively, right? So those patterns that seem not to be easily relatable, they can break them into pieces using all the components and all the machinery of this, and able to combine them to recognize faces in ways that even beat humans in a very remarkable way. But what about financial data? Well, the problem with financial data is that it's highly non-stationary. So what do we mean by that? Well, if I take pictures of a cat, if I take 20, 30,000 pictures of a cat, the features of that cat are not going to change over those 10,000 pictures. So because of the system is stationary, these systems allow to pick those features and those relations very effectively. So the features are not changing. So all the sets and all the pictures that you take preserve that stationarity. Those relations are not changing. We humans don't, or animals don't change the relations in our faces that quickly, right? It takes many years to do that, right? So that's part of the non-stationarity, that part of the stationarity properties that these data sets actually offer. The same thing is with language, right? Language is, even though it sounds complicated, and the structure of how we speak hasn't changed over 100 years. I think if you pick documents over the 100 years, they pretty much grammatically, they will have the same structure, right? And these techniques are able to find those patterns very effectively again. And then we have been able to get a lot of ways of quantifying those words. But the structure of the language is what these techniques are actually picking. So the way we compose words, we compose sentences, is very much, has been the same for many, many, many years. So that's about what the success of these techniques have been, and then how they have been applied. That combined with a lot of computing these days is something that has changed a lot of things. So just to go on into that idea that if the patterns of a face or of an image generally don't change with time, so if you can take pictures of somebody over some period of time, those patterns are going to remain pretty much. And these techniques will allow you to do that, right? So think of it like you input many, many, many pictures, and those pictures, if they have the same relations, they will be picked up by these techniques very effectively. So what is it for financial data that is so hard to track? Again, it's the non-stationarity part of it. So there's a lot of techniques that have been used, what is called in time series analysis, but they have been very relatively successful in univariate relations, so single time series. So for example, we have the ARIMA models, which if you put one time series and it has some seasonality in it, these models pick that seasonality very effectively, right? But when you have multiple assets, or when you have multiple time series, those techniques become very difficult. And the reason why is because those relations, again, are non-stationary, so they could be mixing, right? They could be, for example, one relation 2-3 days ago could be changing the relation of something 1 day or 2 days after. So that kind of relation, that kind of complexity is what makes these techniques a lot more challenging. So data is highly non-stationary, and the other way that you can think about it is that they're highly adaptive, right? So if you think of a system that is actually responding to news or responding to new market conditions, the market move in a way that they keep adjusting so that they adapt to those new market conditions. So it's constantly changing. Right? So you can see that in assets, right? When you have a portfolio, a lot of the techniques that are used, for example, in handling portfolio, like a price, right? They start with saying, okay, well, you have a fund like the S&P. You have 500 assets, and those 500 assets have prices. They fluctuate, right? And then they try to model the fund by using regressions, right? So the big assumption that you do when you put a regression on a particular fund is that the weights of that fund don't change over time, or at least they don't change over a period of time, right? So when you do a regression on these 500 assets, you're going to get a number, but that is assuming that the structure of that fund doesn't change over those, whatever window you use, like 30 days or 100 days or 500 days. But the reality is that those assets get rebalanced all the time, right? So the weights in this portfolio change constantly, right? So in some ways, if you think about your coefficient that you're getting out of that regression, in reality, it's changing constantly, right? So in some ways, these techniques allow you to sort of average those relations over time. But in order to capture the movement of the rebalancing of these portfolios, most of the statistical techniques become very challenging. So markets tend to be moving a lot. People rebalance their portfolios often. And then on top of that, people move money around portfolios. So it becomes a very complicated, very intricate moving web that is changing constantly over time. So the challenge then is to say, okay, well, what kind of techniques can we use to actually look at that? So then the problem is how we can transfer that power of AI to look for patterns in time. So at the end of the day, all of these techniques are nothing but recognition of patterns. But if the patterns are changing in time, these techniques become a lot more challenging. Right? But then we can go back to physics and give us some light in how physics handle this type of problems, right? And then physics is specifically very good at looking at dynamics. I'm looking for patterns in time. Now, the reason why physics works, in some way, well, it's kind of a bold statement to say why physics works, but in some ways related to AI, is the reason why the dynamics are detectable of an object is because they have this concept about, I don't know how many of you have gone into quantum field theory or anything, but there is something what is called an action principle. So the motion of an object in nature seems to respond to an action, right? So we have the differential equations of motion and all that stuff, but in reality, when you look at the big drivers of motion, what you have is an action principle that is driving. For example, when you take a telephone and then you let it go, we know where it's going to go, right? We know that it's going to go down. It's not going to go up, or it's not going to go to the sides, because that object is responding to an action principle that is making it go down. So in some ways, that action principle is actually doesn't change in time. And that's the beauty of this. That action principle is pretty much constant, right? The relation of the action principle stays the same. Now, what is the analogy to new techniques in AI these days? Well, I don't know if you have seen a lot of these things that we go with reinforced learning. So reinforced learning has two concepts. One is the transition matrix associated with the changes in movement, and the other one, they have like what's called a reward function. So that reward function stays constant. So the pattern of time changes, but the reward function stays the same. And these systems that they have developed, for example, like the driverless cars, or some other techniques like robot trading, what they do is they keep a constant reward system. And then the AI techniques learn how to keep that reward function and changing that transition function to optimize the strategies that you're actually looking at, or the motion of the car for that matter. We humans seem to be following the same idea. For example, when we try to walk, we are doing exactly that, right? So we just make steps, and then we correct a reward function inside. If the step works, and that reward function seems to work, we seem to weigh that step more. And if it doesn't work, we just downweigh that action more until we figure out how to walk, and then we wire that into our heads, and then we end up running afterwards. But it's the same sort of idea, right? But then in the concept behind it is that we are looking for a reward function. The reward is to be able to walk. And then we keep upgrading, we keep optimizing that reward function. Physics is not that different in the sense that the systems seem to be updating and minimizing that action function, which is what drives the motion of a particular physical object. What is interesting about markets is that they are not just like static pictures. They are more like, I think I use a very strong analogy, which is called the school of fish. So markets are constantly changing. That relation of the objects is moving constantly. And then the market moves, but the relations among those assets are also moving constantly. So if you take pictures of the school of fish, right, and then you take pictures, and if you put it into a neural network, right, you're going to see that the neural network is not going to be able to pick any relations because it assumes that those relations are stationary. But the school of fish is moving constantly, right? So that shape, the face is moving, becoming larger or smaller, and those features are moving within each other. So in some ways, markets are very similar, right? So it's like a school of fish. And there's actually some interesting research that has been doing and studying the behavior and the migratory patterns of a school of fish, which actually could be translated to market in some ways. And we'll just go over that in some kind of heuristic kind of example. But the idea is that, yeah, in reality, markets are dynamic, right? They are adjusting constantly. For example, in the school of fish idea, they have done studies that say like that some fish, for example, they behave very independently after one point. And there are some conditions like the temperature, some temperature gradients in the sea, and sometimes of the day, some light components of it. And then all of a sudden, the fish sort of are all spread out. And then there's a critical point in which they get together and they just migrate in a kind of cohesive group. And when you study the dynamics of the group, they actually, they find that, for example, it's like, I don't know who is cycling fan here, but if you follow cycling, you see the dynamics of the pelotons are very similar to a school of fish, right? So for example, the people inside the peloton, they only worry about, they're not worrying about their wives, or they're not worrying about winning the race for a period of time. They are worrying about keeping the distance with each other to be effective, right? Because that way they don't crash into each other, right? So the objective of the person inside the peloton is to be able to keep that distance with each other stable. And then in a way that, so that characterizes the dynamics of that particular one inside the peloton. Outside the peloton, the dynamics are a little bit different. They are actually moving to like get over the next, and then there is a different reward function for that particular kind of entity of that peloton. So fish has some similarities in that dynamics as well. So that's kind of the analogy that we have with markets. Again, and one of the techniques, and then I don't know if you are very familiar with some of the driverless cars techniques that they use to detect moving targets. But one of the techniques they use is, okay, they identify the target, and they identify it by image recognition in some ways, and then they put it into a process that analyzes the movement of the market. So some of these techniques were very similar to what they use, for example, in the Apollo program. They introduced something what is called Kalman Filtering. So the idea there is that in order to keep track of the rocket, they needed to have a certain level of precision and actually be able to infer or predict where the trajectory of the rocket is going to be. But there's a lot of noise involved in that process. A noise in the measurement of the tracking device, and also a noise in actually the movement of the rocket. So they came up with something relatively simple and very elegant, which is called a Kalman Filtering. And by that, they managed to track the movement of the rocket very effectively. So it's sort of similar idea, and in a way, it gets to a problem that is called inferences, and then they use a lot of that in a very similar way. So in some ways, in some aspects, AI is doing some of this already. It's looking at the idea of the school of fish. The only problem with this is that when you take a picture of the car, in the real markets, that car might be changing, right? The structure of that car might be changing. So the problem is still a bit more complicated than that, but it's sort of getting to that point, right? So what is it that the car is doing? Well, we can go back to physics, and then give us some hints in how dynamics move, right? So how do dynamics move? We can start with a very simple example of a spring, right? Spring moves in time, and if you take pictures of the spring, you're going to see different locations of that spring, right? So it's moving in time, It's a simple problem because it's bounded, so it comes back and forth very nicely. But at one point it was hard because it was kind of a motion that it was hard to understand, but it's a moving motion. And what is the solution for this? Well, most of you probably know. It's a second-degree differential equation, right? If you take the second differential equation of that spring, you're going to pretty much describe the whole motion of this, and it becomes a sinusoidal relation. So it becomes a little bit difficult because you have a second-degree differential equation in there, so you have to use differential equations. It becomes a little bit involved, but you can make this very simple by decoupling the velocity from the position of that spring. By doing so, you put that into a matrix representation. Okay, it goes to TensorFlow again, so start seeing the power of that in some way. And if you do that, the problem becomes relatively simple. It's just the solution becomes the exponential of a matrix, which on that matrix is that transition matrix. Right? So, and this is the solution of that system, right? And then you can express that as an exponential of a function that moves in time, right? So in some ways, the way you can think about this is that transition function is the one that takes the system from the state A to a state B to a different time. Once you come up with the transition function, you pretty much have gotten a lot of the problem solved. So a lot of problems are actually falling into this category in which you can linearize your problem very effectively by decoupling or by differencing your time series in some way. So ARIMA is a bit like that, but not quite, because it doesn't have the mixture property of your lagging variables in a non-linear way. Right? So the matrix multiplications allow you to capture that nonlinearity in a very effective way. But you can differentiate your time series multiple times. You can put it into a vector form, and you can do matrix multiplications, and then that linearizes the problem quite effectively. So that starts picking up some of those patterns in time, right, that have a structure, right? So they may be moving, but in reality, the fact that they're moving, they still have a structure, and then you can use some of those techniques to pick up that structure. So you can have multiple input parameters. This could be lag variables, and then the structure of your matrix gives you pretty much the dynamics of that in time. Right? So in some ways, they're picking the patterns that the system has in time. So you just make the problem to look for patterns that are moving in time. And if that structure or that motion has some dynamics to it, this should be able to pick that up more effectively. And then some of those techniques, you just combine them into nonlinear relations, and then you pretty much can. So in some of the work that I have done in the bank, we have used some of these techniques, and then use deep neural networks with actually quite I cannot give you a lot of the details of that, but in some ways, this is some of the things that we have done. And then this leads to a very architecture that you pretty much are familiar with, which is recurrent networks, right? And why is it the recurrent? Because of the nature of the recurring pattern on this, right? Because they depends on previous day, and this depends on they give you the transition of the previous day. You can embed that into a recurrent network, and this allows you to analyze the structure more easily, right? So if you have a multivariate system, you can put it into this, and then actually picks up some of that very effectively, right? In some ways. Now, some of the problems are not that simple, right? And not that easy, right? The reason why is because there are two observations here, right? And again, the same thing, the same idea with the rocket, right? The motion of the rocket could be noisy, right? And the measuring and the detectors that measure the motion could be also noisy. You have two sources of noise in some ways, right? So you might have a noise in the transition function, and you might have a noise in the observation, right? So that becomes a very difficult problem to track, but that's where the Kalman filter sort of came into the picture and then solved that issue. But with the Kalman filter, it is a very structured model. It's a very parameric model in some ways because you need to provide the structure of the metrics, right? So in some ways, you need to kind of know what that matrix should be. So that is kind of the downfall of the, and then it doesn't really have you have to modify that methodology to look for the complex structure, right, of the dynamics of the parameters. But it can be adapted for that, and then some of that can be used for these things. But that issue about the two noises of that leads to an inference problem, which is somehow trackable, but some of it is not. And again, this can be variations of this, right, have been used in reinforced learning, right? So again, the idea is that the reinforced learning allows you to actually figure out what these parameters are in time, because you can embed that into a deep neural net, right? And then those relations can be actually tracked. And then the system can actually figure out what the parameters of that matrix could be, right? I don't know if you have read about the game of Go. So what they did is they actually put it's a relatively complex system, but they embedded the possible states of that game, right? And the machine learned how to do it. Why? What was the big trick of that? They put a neural network behind to figure out what the transition function is that gives you the ultimate set of states for that transition. And the system eventually learned itself and picked it up amazingly well. So to the point that, unheard of in the past, this machine could actually beat the best player of Go in the world, which was like a huge treat. And because of that, Google bought them for $500 million or something like that. So that was a big, and the amazing thing is that all these techniques have been around for a long time. So reinforced learning has been around from the 650s or whatever. So the big innovation that they did is to put a deep neural network in defining that transition matrix, and that turned out to be magic, right? So in some ways, all these nonlinear, non-local relations that were optimizing that kind of transition function, the neural network could pick that up. In addition to the fact that it was, in the fact that this gave you that recurrent relation that we see when things move in time, right? By the way, if you have any questions or any comments, or just I'm hoping not to hold you here for too long. I think some of you want to go and have refreshments today and have some wine, so I'm not going to be boring you too much with this. I'm hoping that the math should be light, and just to illustrate the points, I might just give you some ideas of the things that we have worked on that have worked applying some of these techniques, but I'm not going to get into a lot of the details of that. So again, what I was trying to say before is that this becomes an inference problem. You have a system that you can actually, that potentially might have some level of noise associated with that. So the transition function might be having some noise issues, right? And then, again, you can translate this into this with some kind of noise, and this becomes a matrix, right? And then from this, these observations can actually lead to the model that you're actually tracking. Now, the issue that you have also here is that these variables could be hidden, right? So that means that these are variables that you don't see, you don't observe, right? So in principle, going back to this fun idea, right, you can see that if you want to, for example, model or create a model for a simple fund in which you can actually try to infer how the weights are changing, then those weights, if you cannot keep track of the rebalancing activity of that fund, you can put those weights as hidden variables, right? And then by the price of the fund that you observe, for example, if you have an ETF and you see the components of the ETF, you can in principle infer the weights as hidden variables into that process. So that's sort of kind of the ideas that you can get out of that. I mean, it's not going to be super perfect, but it's actually a pretty good environment to work on this stuff. So just give you an example, so going back to this idea, right? So a lot of the techniques that they're using right now is that, first of all, they try to identify the object and put it into some kind of Kalman filtering idea to decipher the motion of that object. And in that way, they see that the car is moving and they can predict or at least track where the direction of the car is going. So some of the Google cars have been doing that, or the driverless cars. some variations of those techniques. So how did they do it? They put a neural network, like a convolutional network, that identifies the object, right? And then the network, or the Kalman filtering system, which is going to be here, sort of takes that and then looks into the motion of that object. And they're able to track it that way and identify with the motion of that particular system. So it looks complicated, but in reality, it's just more matrix multiplications and some inferences, right? So again, you have to probably track the hidden variables in there and keep track of those hidden variables, but it's a trackable problem in some ways. So what is it that Kalman filter gives us? Well, it allows us to track the motion of some objects, right? But it's a parametric model, so you need to sort of specify how that transition function, or at least the parameters of that transition function are. So even in this particular scenario, some of these transitions are derived by physical motions, right? So those transition functions are derived by physical motion. So probably when they do these things, they put that kind of physical motion into those parameters. So you need to have a parametric model. The motion, the hidden variables are hard to track. So you sometimes don't know what are the hidden variables in a very dynamical system. So they're usually hard to track. And then the other part is that, again, with the school of fish idea, right? Some of the tracking of these images, right? They assume that the images don't change. So they track the image and then they can move in time. But with the idea of the school of fish, the image also might be changing and moving. So that is the challenge of that. So in some ways, like back to the fun idea, the weights are changing constantly, right? So one of the other things that we would like to find out is how can we model those weights or those changes in time, because that happens quite a bit. And now, why is that important just besides the fun dynamics? Well, there were some serious problems on the 2007 that people didn't quite understand. And then some of those problems were led to the lack of understanding about these correlations. So I'm going to give you an example of why that is an important thing. Back in 2007, people were playing around with mortgage-backed securities. So what is a mortgage-backed security? Well, it's a pool of mortgages that they have from some kind of individuals with certain similar credit conditions. So what they were doing is say, okay, well, we're going to put a whole bunch of people who have very high likelihood of defaulting. We're going to put them into this pool of securities. And out of garbage, we're going to come up with gold, right? And that was the genius of these securities. You say, how did they do it? Well, a very simple example is like this, right? You have a note, right? And they give you a probability of paying you $1,000 with 70% chance. That's pretty bad, actually. That's worse than junk status, right? If you're going to write a note and you only have 70% of getting paid, that's pretty bad. So it's kind of junk status. And then what they did is they just put like a lot of the similar ones into one pool, right? And then you have another note, same idea, right? Same description, same probability of default. And what they did is to say, okay, well, we're going to be smart, and we're going to say, okay, we're going to structure a payment structure out of this in such a way that if one of the members of this one pays, you're going to get the $1,000. So you have what is called tranches. You have the higher tranche, and then you get paid first. Right? So what are the chances of you getting the $1,000? Well, there are three possible outcomes to get the $1,000. Both of them pay, right? The chances of that is 0.7 times 0.7, right? The other chance is that one pays, but the other one defaults, right? So in that case, you still get paid. So that probability is the probability of getting paid and the probability of default, right? But there is another chance that one defaults and the other one pays. You still get that $1,000, right? So by doing so, your probability goes from 70% to 91%, right? So from being a junk bond, it became a AAA bond. And that's how they actually were spreading this. So in reality, they were spreading risk with this kind of structures. And they were very appealing because they were even insured to be AAA, even though they were coming out of junk bonds, right? It's just because of the structure of this thing was such a clever way that coming up with AAA structures out of something that it was really a pool of junk, right? So, and then the default probability went down to 9%. That's pretty genius. That's a pretty amazing thing, actually. And actually, it has a lot of use, this thing, because it allowed us to spread risk. The only thing that they forgot about is, well, actually, some people probably kind of felt there was something going on here, but some people didn't quite embrace it because they were making too much money. And in financial markets, what you see, while the party's on, nobody cares. Is when the music stops, is when people really say, oh my God, I think I made a mistake. But in any case, so that happens quite a lot. So they were partying a lot. They were making tons of money with these things. So everybody was enjoying life. But then they were making a big assumption with here. And then they were making the assumption that these two things are not talking to each other, right? That they're independent, right? So if they're independent, they do behave this way. And this stuff is quite actually smart. But if they start talking to each other and they start behaving like the school of fish, right? They start getting together and they start behaving similarly, this thing becomes super dangerous because if they start having the same correlation, then they behave the same. So your probability of default goes from 9%, go back to 30% really quickly. So it's a huge correlation risk that these models weren't actually embracing or modeling that well. So again, it's that idea of the school of fish. Markets are dynamic, so all these components were moving, right? So these correlations do move in time. Sort of similar to the fund, right? They move because the relations do change in time, right? So they forgot that part, so the correlation risk is a huge deal, right? So it's similar to that idea of the school of fish. Those things are moving, and so one has to be able to track that in a realistic way. So some of the, and just to finish, for example, that has definitely impact in pricing, right? Of course, if you have a bond generally is priced, you discount the bond for a particular risk-free rate, right? And if you have a probability of default, you multiply that by that probability of default, and then that pretty much adds up to the rate. And then a lot of bonds reflect that, like the risk-free rate time plus some kind of probability of default in some times. And of course, prices fluctuate quite a bit because of that. For example, the single node will have a totally different price than the, but if the correlations are moving, right, this probability is going to change. It's going to be moving, right? So an interesting application of this, if there is a way that you can actually model that correlation risk in time, then these kind of structures could become very powerful, right? So, and there are some things, again, going back to this idea about inference is hidden variables. If you can, from pricing, right, if you can infer what those dynamics of those correlations are in time, then some of these things can be very powerful in general for different aspects of finance and lending in somehow. Right? Okay, that was pretty much the end of my talk. What I wanted to say, like, I'll give you a couple of kind of projects that we have been working on similar to this, where we have been able to use some of these things. For example, we used a deep neural net, a recursive neural net, to do a similar problem like this in some kind of borrowing rate scenario, and we were able to predict the rates much more effectively. It's never 100% sure, but much more effective than any ARIMA model or any other model that we have seen. So there is a power in terms of what is called, the only challenges with this is that the amount of the data set that you have could be, you need large data sets. So in some ways, when you have a single security, generally you don't have more than 3,000 or 4,000 points for this because the history is not that large. But one technique that you can use is to pool those securities into, again, portfolios, and then that gives you, like, that expands your data set significantly so that you don't run into problems of overfitting. So that's one of the things that we did there. Another one is in terms of pricing, right? So I said before that pricing is also another part in which this could be very powerful. If you have, for example, if you have like a security for which these parameters are changing with time, then most of the models that you find out are going to be very hard to track, right? But if you can actually monitor or actually infer what those changing parameters are, then you can use either AI techniques or even traditional quant models to come up with those prices. So there was a paper that I had back when I was in Baruch, in which we actually did that. For example, if you have a company that's going through a merger, so the company that's going through a merger, you can think of it having two single states. One, when the company is going to go through, you're going to get some money out of this. And if the deal fails, you're going to get another different state, right? So the question is that the system seems to be changing between these two states, and people are actually pricing the probability of the deal going through. So if you state the problem like with the changing probability of the systems, then you have a similar thing like the coupling or the correlation of these two securities are actually hidden from the market. And you can infer them. And then with that, you can actually price options on those securities much more effectively. And actually, surprisingly enough, it reproduces the smile very effectively. Right? So again, it's because you are modeling the correlation in time. And since the correlation is moving, then this actually allows you to track the problem very effectively. I think that's about it for my talk on it. If you have any questions or any comments, very welcome. Let me see. Yes.
So it seems that there's obviously two schools of thought, more quantitative analysis and fundamentals and investment analysis. Do you see those two coming together effectively? I mean, I know there's some blending, there's risk attributes that are being pushed into fundamental modeling exercises, but how do you see those coming together?
So let me repeat the question. So they say that he finds that there are two kind of school of thought or two regimes, I will think, right? In which one is modeling risk in some ways, right? And then the other part, I think, to rephrase, is the pricing part of it or the predictability part of it.
Let's call it quantitative trading analysis.
Okay. Quantitative trading is going about prediction. So when you predict something, again, you need to have that kind of structure in time, right? If you cannot detect the structure in time, it's going to be very hard to predict something in the future, right? So again, that goes back to that idea that if you can figure out what that structure of time is, right? If you can design your models to detect that structure of time, then you can infer what the next, on average or statistically, what the next movement of the market is going to be, right? So now, that is in prediction, which applies to trading algorithms, because if you cannot predict, you're not going to be able to do too well in trading, right? There's been some techniques on that using reinforced learning, in which they put actually a robot to learn what's the optimal P&L strategy, and then they actually picked some of the strategies relatively successful. Some of the secrets that some hedge funds have been working on is along those directions. But these same techniques can apply to portfolio management, right? And I don't know if you know about the CAPM theory, right? The CAPM says that the pricing of an asset on average is nothing but what the market gives you, right? So if the school moves, it's not the movement of the asset that matters, it's how much the fish contributes to the market, right? But then all these theories are assuming, again, that you have that static relation between the asset and the market stays the same, right? But if that relation changes, the correlations are changing over time, then you might have some noise associated with the cap. I think there was a talk also, the second talk was talking about the beta. And if the beta is changing over time, right, then there's a potential risk that you are actually not associating with your strategy when you do portfolio optimization. So it's the same kind of idea. If you have like a correlation that is changing among the asset and the market, or like the beta is changing, if cyclical or it has a time varying component to it, you may be making you may be leaving a lot of risk in the table. And then your strategy to optimize your portfolio might be changing because of that correlation movement. Right? So that correlation risk. So I think some of those problems are very similar in some ways. Right? Again, it goes back to pricing as well. For example, if you're pricing a derivative that is potentially in a relation of 3 or 4 assets, that correlation risk matters a great deal. And again, in this case, right, with the merger, that correlation risk is really what gave us the smile that we saw in the market. Without coming up with any stochastic volatility problem, it was using very simple option, Black-Scholes formulas, just modeling the correlation, how it changes. That turned out to be super powerful. So it applies to pricing, applies to portfolio management, applies to forecasting. Yes?
When you use deep neural network to do this price prediction, we find regardless of how much data you have, it's very easy to overfit.
Right, that's why
By signal.
you're right. Right, so that's what I'm saying, that we do like a lot of grouping. So what we do in order to expand the data set, we make, well, but then you have into the same, when you do cross-sectional fitting, then you run into the same issue, kind of, right? So what you do is you assume that you put a pool of securities, and then you assume that those pools are behaving similarly, at least to capture that kind of dynamic in time. And if that's the case, then the whole set will expand, will augment your data pool at the same time capturing that kind of dynamics in time. And it worked pretty well. Again, I mean, there are some techniques that we need to introduce to be able to introduce the idiosyncrasy of each security in there, but the pooling behavior is there, right? So by just putting a pool, extending your data set by 4,000 securities, that worked out pretty okay. That the assumption there is that those securities are behaving in a very similar way. Yes?
How do you compensate for securities that are asynchronous trading? For instance, bonds are far less liquid than stocks. So a bond might trade once a month or once a week at different times. So how do you factor in asynchronous time series?
That's a very good question. There are different ways of doing that. There was another paper, another talk, in which they were talking about illiquid assets. So there are some techniques in which what they're doing is they're using AI to be able to infer illiquid assets, illiquid prices from liquid assets. Again, it's using that relation. If you know what the relations are in time, right, of the assets when they are liquid, right? So when they trade, and you see all the ones that trade with it, and then you can infer prices out of that, out of the movements, like again, this web, right? If this moves, and then it's affecting me, when these things trade, and then I see how it moves, then when this doesn't trade, but this do trade, and I can infer that and come up with an inferred price out of that. So there was a talk about that in the previous session. So you can use that. You can get the inferred prices for a particular time, right? And then use this to look into the dynamicals of the rest of the thing. Right? But actually, it's actually the same kind of problem, because if you think that all the assets are in this kind of web that is moving, right? That web, whenever this moves, in principle, should move these ones. If that dynamics is constant, it's like a field, right? If that dynamic is constant, it should be persistent in time for a while, right? So it's the same idea. So if you model it like that, then it's like a whole co-movement. Right? Now, again, to relate this to other type of research that is happening outside finance is like network theory. Networks in social environments, something that is becoming very, very popular right now. But if you think about what we are as a collective entity, right? Humans, I mean, I'm talking about, and what they trade, we're nothing but reflecting social connections, right? And then these assets, when you put them to this kind of web of things, they're reflecting that kind of changes of social connections. And you can put that into a network analysis and start seeing that dynamics very effectively. So that's something that is that I have been working on, but it's quite fascinating, that stuff. So there's a lot of work, for example, like in the realm of, for example, if you are upset and if you are like in a bad mood, right? They have done studies, for example, is that you might be very happy and then you go and see somebody who's really upset, you get affected by that and then you potentially can get also upset or sad, right? But they have done other studies, it's like the immediate connection is obvious, but if you go and if you meet a person, right, who has met another person or another person who has been angry, then by the third level connection, you actually can also be upset because of that, even though you haven't met the person who was originally angry, right? So, and it's because of how we are connected as a network. I mean, it's like all these connections are really matter a great deal, right? So if you can monitor that, so even a third relation might matter to how your mood is and how you react to them, to certain conditions, right? So that kind of network analysis is very fascinating in that respect, right? Yeah.
So you mentioned about machine learning.
Sorry, I didn't hear what?
You mentioned about reinforcement learning.
Oh yeah, okay.
So I'm recently also working on this topic.
Yeah.
I'm trying to use it for portfolio optimization. Let's say the action space would be very large sometimes. Suppose you have a lot of assets in the portfolio. Just want to learn the insight from how do you overcome this?
Okay, so that's a good question. So for example, again, this could be thought of hidden variables. So if you have like a multi-axis hidden variable, but you can actually reduce your space to a handful of hidden variables that you can think that it's like when you do PCA or principal component analysis, what you're doing is you're rotating your system into an orthogonal set of variables that could be lower than the actual original set, right? So you can reduce that, and by reducing that, your problem becomes more trackable, right? And the noise can become more trackable, right? So the question is what kind of orthogonal sets you're going to be using for that. That's the but.
Action space, let's say for individual asset portfolio. I mean, buy, sell, buy one share, sell one share, buy two share, sell two share. So
Yeah, but that's a very local level, right? So if you think about, for example, think of a portfolio. Going back to this action principle, right? There is somebody making decisions about the relocation of that portfolio. Now, that person is responding to a strategy and can guarantee you that that strategy is not changing over time. So think of the reward function. What these systems can actually do in reinforcement learning is actually figuring out what the reward function that the portfolio manager is using. So, but the amazing thing of this is that strategy for that portfolio manager is not changing in time. That stuff is, I can guarantee you that he doesn't come on the morning and say, oh, I'm going to change my portfolio out of the blue. He has a strategy that he has been following, and that most likely is going to be constant over time. And then what these systems are doing is picking up that kind of strategy indirectly, right? But if you think about it, if you try to do it at the individual level, you go crazy, right? At the buy, sell. But these techniques allow you to like see how the transition of the market moves, and then figure out the optimal actions to take to optimize that reward function, which is constant. That's the constant part, right? Again, let's go back to physics, right? If you see a stone dropping, it follows an action principle, right? I mean, you have Newton's FMA law, but they have done more work on this. And then we go to field theories. The reality what is not the force equals ma that really is at play. It's the action principle that is at play that is determining the motion of this object.
So the reward is constant, but you still have to update Q every time.
Yeah, of course. Yeah. And again, it's an adaptive system so that the ways are changing over time. And then, okay, here's the other analogy that I have. For example, if you start taking pictures, right? Most likely, if you take 10, 20,000 pictures, again, those features don't change of that particular cat. But do this, I cannot do this experiment, but think of it in a thought experiment. Let's assume that you can take pictures going back 100 million years ago. And you can take pictures every 10,000 years. So if you start taking the picture of a lizard, you might end up with a cat. Well, if evolution is right, there is a dynamics on that transition that if you set up the problem right, it should pick up that transition very effectively. If evolution is following a reward function, which I think it is. right? So you can see the transformation from the lizard to the cat in time. But then you need to add the transition function, otherwise you're not going to pick that up. If you put that into a regular convolutional network, it's going to get noise. But there is a pattern, right? It should be, because evolution sort of brought us to where we are for a reason. Right? That's kind of the other analogy that I use for this. And again, it's modeling that transition function, really. But even the transition function can change in time, right? For example, these parameters can move in time as well. So, but that's what I'm saying, the hidden variables, if you do stochastically model them, you can actually potentially pick that up. I'm not saying it's an easy problem, but you could potentially pick that motion in time. For example, a fund manager, they rebalance the portfolio every day. In principle, that information is there, right? So it's changing. The whole nature of the whole thing is changing. So if you can keep track of the rebalancing every day, you can figure out the whole dynamics of this portfolio. Any other questions? Yes.
So you have for one slide talk about adding the filter, the Kalman filter,
Mm-hmm.
so into the neural networks, right? So why that help? So is that the neural networks is not going to capture information?
The reason is because again, as I said here, right, you have reality two systems coupled together. One is the state system that is moving, right? In other words, the system that takes care of the transition of the switch from one state to the other, from one time to the other. So you can think of this, for example, this takes you from t-1 to t, and this is the way that the system gives you that transition, right? So, but that system could be different from how you take the measurements. So from this relation to this could be a nonlinear, very complex function, right? So decoupling this in time, that's what the Kalman filter does. Taking away, it's a filtering system in the sense that it takes away, it figures out the state variables in time, and then by looking at the measurement that you see. So like the rocket. So they can actually figure out what the transition is, what the dynamics of the rocket is, by filtering out the noise in both processes simultaneously. So it's keep an update about the volatility of both systems, and they keep updating them until they keep reducing that. It's similar to reinforced learning in some ways. That's what reinforced learning does. So you start with a state that you put it as random, and then with time, it keeps updating the system so it keeps having a better inference of the distribution.
You do have capability to measure the actual place.
Yes.
So you take the difference between the measure and the estimation. So you have to able to, in this way, are you able to measure the true value versus your estimation for every step?
Estimation of the true value.
You cannot really do the correction, right? So you have to reinforce on every step.
Okay, I give you a problem that I worked on. Again, so for example, so the way we did it is again, go back to the merger paper, right? So we stipulate the system to be a state of two variables, right? The stock when the merger is going to go through and the stock when the merger fails. So we assume that those two systems are kind of independent. And then what connects them is the probability that the market is pricing this to be. So it's kind of, think of it like in that way, it's a correlation between those two states, right? And then the price of the target company is a reflection of that state. So it's like a highly nonlinear system, but it has the correlation moving. So so there are three different states. The price of the stock when the deal goes through, the stock of the price when the deal goes through, and the probability. So the probability moves stochastically. So those three become your state variable. But they're hidden. So the only thing that you see is the target company and the option on the target company, right? So in that case, this is the observable, right? And then there's a complex function between those three state variables, right? They becomes complicated. It's highly nonlinear because of option pricing and all that stuff. So, but then if you state the problem this way, you can actually infer the state function out of that, out of the observations. For example, if you take like 5 years, or maybe not even that long, like about 4 or 5 years. No, but the mergers, when they get announced, they don't last that long. They last for like about 5 months, the tops a year sometimes. But with that, you can infer the 3 state variables very effectively. Well, effectively at least. Huh? You see what I mean?
Yeah. You're going to change, assuming the probabilities keep changing.
Exactly. So it's like an inference problem in the sense that you start with, it's like what Google does the same thing. For example, when they do the page rank algorithm, they do exactly the same thing, but they start with some probability, and then dynamically they figure out the probability by just keep reiterating that. It's the same idea. And then they reduce until they figure out the probability quite effectively. Right. Oh, okay. Thank you.